This is the second lecture for Chapter 7, and this will cover sections 7.3 through 7.4. I want to start off with an example, or a homework problem on ESP. And this has been a problem that we've talked about throughout the course. A classic experiment to detect ESP uses a shuffled deck of 5 cards. One with a wave, one with a star, one with a circle, one with a square, and one with a cross. A total of 10 cards will be drawn, one by one, with replacement from the deck. The subject is asked to guess the symbol on each card drawn. If a subject actually lacks ESP, what is the probability that he or she will correctly guess the symbol on the card? Well, that probability is going to be, since there are 5 cards, and one is correct, the probability is going to be 1/5. Part B, if a subject actually has ESP, should the probability that he or she will correctly guess the symbol on the card be smaller than or larger than the same, or the same as the probability in Part A? Well, we would expect the probability to be larger than the probability in Part A because we'd expect the person to get more correct. Part C, Julie thinks she has ESP. She wishes to test the following hypothesis. The null is Julie does not have ESP, so the probability of a correct answer is just 0.2, and that's 1/5. Julie, and the alternate would be Julie does have ESP, so the probability of a correct answer is greater than 0.2. So Julie participates in the experiment and is right 6 in 6 of 10 tries. You are asked to test, at a 1% significance level, the hypothesis that Julie has ESP. Design and carry out a simulation to estimate the p-value, that is, the chance of getting 6 or more correct answers out of 10 if indeed Julie was just guessing and does not have ESP. Based on your estimated p-value, what is your conclusion? Okay, so I actually wanted to demonstrate this problem using the calculator, and there's actually a few different ways that we could do this. Again, this is an example where we're going to be sampling from a uniform distribution. And so one way to think about this, as we design our simulation, one of the things I think we want to think about is what random number generator to use. I'm going to code it random int 15. And my sample space here is 1 through 5. Now, we're going to be a little bit creative here in how we set this up. So we're going to code as follows. All right, so 1 will be success, 2 through 5 will be failure. Notice in this way, if random int produces a 1, that's a success, else is a failure. There's 5 possibilities, so this is going to simulate a success rate of 20%, or 1/5. So let's go to the calculator here, okay? Clear out what we were doing previously. And so here's how the simulation would go, okay? So I'm going to go math, over to PRB, choose random int. This time we're going to go from 1 to 5, and I'm going to not define an end to start with. I'll paste that in because I'm going to look at the simulation one at a time. So press enter. That's a 1. That's a success. That's a failure. That's a failure. That's a failure. That's another failure. So far I've got 1 success in 5 tries, 6 tries, 7 tries, 8 tries, 9 tries, 10 tries. So that would represent an x value of 1. So if I defined my x value, or my variable x, okay, so x is the number of successes. And so far, we had the first simulation resulted in 1 success. Going back to the calculator now, I could do this again, 10 more. I could do another iteration of 10 tries. Remember, the calculator is just guessing. There's a success, 1 out of 5, 6, 2 out of 7, 8, 3 out of 9, 3 out of 10. Okay, so I go back. This time I got an x value of 3. One, that's a failure. 2, 3, 4, 5. There was a success, 1 out of 6, 7, 2 out of 8, 9, 3 out of 10. Okay, so this is one way that I could do the simulation. And again, this is rather cumbersome. It takes quite a bit of time. Now, I wrote a calculator program that will actually do this simulation for us, okay? And I want to show you how it works. I'm going back to the calculator right now. And one of the things I want to point out to everybody is that the list feature, go to the list editor, I press stat and go to edit, okay? Now, I'm going to clear out L2. I'm going to use L2 for this example and talk about this. Now, if I put, say, a 1 here, and then a 0, and a 0, and a 0 again, and I put 4 zeros in list L2. So now I have a 1 and I have 4 zeros. So notice if I consider the 1 success and then the 4 zeros failures, then that list represents a 1 in 5 probability of success. And here's what I want you to notice. See how each one of these now is coded. L2 5 is 0. L2 4 is 0. L2 3 is 0, and so on. Now, if you think about it for a second, let's go back to the home screen. If you think about it for a second, random int 1 5 was giving me those 1, 2, 3, 4s, and 5s. So in other words, if I were to go and do my simulation, if I went to probability, chose number 5, same thing, okay? So I'll just paste that in, and I press enter now. I just got a 3. Well, notice if I go to L2 of 3, the calculator will actually print out a 0. Now, it turns out I can actually embed the random number generator right into the L2 function as follows. So I just typed L2, and I'm going to go and choose random int number 5, and I'll paste that in. Everything stays the same. Close the parentheses there. Now I press enter. That was a success. That was a failure. That was a success. That was a failure. That was a failure. 1 success out of 5, 2 out of 6, 3 out of 7, 4 out of 8, 4 out of 9, 4 out of 10. Okay, so then I would go over here and I would put a 4, all right, on my graph. Okay, now I could do that over and over again and continually repeat that, but it turns out we could write a simple program on the calculator, which I've actually done. The program's called ESP. Okay, I want to show you how this works. So I'll run the program. Now, first thing it asks me is for the Gesser distribution. I need to enter this using roster notation, and what that means is I'm going to put in 1, 0, 0, 0, 0, okay, and then I'll close the brackets there, and that's going to get pasted into L2. So the calculator just, and I did that by hand in the previous example, but that's part of the program, is to actually put that Gesser distribution in. Number of guesses is 10, and now I'm going to have the calculator do 100 iterations, okay? The experiment's going to be repeated 100 times. And actually, let's do more than that. Let's just do 200. All right. So I'll press enter. Now, what the calculator is printing out on the screen here are a number of successes. You can give the calculator a minute to do to process all of this. And again, remember that it takes the calculator a little while to do this, but think about how long it would take us to do this by hand. All these iterations. I'm kind of looking at the numbers going by, and I'm seeing, you know, most of them are around 0, 1, 2, 3, 4. It makes sense here. Direction of extreme is going to be to the right, so I haven't seen a 6 yet. I'd like, you know, and that is not, that's to be expected. 6, 7, 8, 9, 10 are going to be very unusual under the Gesser distribution. There's a 4, another 4. Keep our eyes out for 6s, 7s, 8s, 9s, and 10s. I'm not seeing any. There's a 5. Another 5. So again, what we see from the simulation is that 6s, 7s, 8s, 9s, and 10s are rare. So what we have now is a list of the number. So what the program does is it stores the number of correct guesses in L5. So that's already, that's happened. And what I'm going to do is look at a histogram. And that histogram I'm going to draw again is going to represent the frequency table that I was drawing earlier in the example. So now the X list I'm going to use is L5 because that's where my number of correct guesses is located. And now the domain for our variable is 0 to 10. Okay, so I'm going to make that 0 to 10. And let's see, Y max, I don't know. I think Y max is going to need to be bigger than 30. I'd probably even bigger than 60. Let's just try 100 just to see. And that's probably too big. I can come by and adjust that. That actually looks okay. I think I'll make it a little bit smaller, the Y max. And again, this is one of the nice things about the calculator and graphing is that redoing a graph is not too much trouble. So this is the Gesser distribution. This is the null distribution or an approximation of it. So now when I go back and I look at the original question, we're asked to estimate the p-value or the chance of getting 6 or more correct answers out of 10. Now for this particular simulation I just did, all right, the estimate for the p-value I did 200 iterations. So the denominator is going to be 200. And when I go back and I look at this histogram, I can do a trace here. And that's what this trace is going to do is tell me how many for each value of x. So notice when I hit trace, the calculator says this bar has a minimum value equal to 0 and the max is less than 1. So this is the 0 bar. There are 19 zeros in L5. Not 19. We ended up with 19 experiments that had no successes. I come across here and look at all the different bars. There's 6. There's nothing there, nothing there, nothing there, nothing there. So in this particular example, actually I can say equals in this case. 0 over 200 equals 0. So that's not a, it doesn't look like a 0. Ah, stupid pen. There we go. So the estimate for a p-value here is 0. Now again, if I did more, if I ran the program for 500 iterations instead of 200, I probably would eventually get a 6 or a 7 or something, and then my p-value would be non-zero. So on problems like these on the homework, the answers are going to vary because again, each simulation is going to be unique. But what this tells me is, one thing I can take away from this is that the p-value in this situation is small. So getting 6 out of 10 is fairly hard to do. And again, if we're thinking about the p-value, it's what's the likelihood of getting at least 6. And so in any case, that's the basic idea for this problem. So let's go through some other information about probability and some basic rules. Let's talk about basic rules. So any probability is always a numerical value between 0 and 1. The probability is 0 if the event cannot occur, if it's impossible. And the probability is 1 if the event is a sure thing, meaning it occurs every time. So using some math notation here, what we say is probability of an event A is between 0 and 1, including 0 and 1. 0 is impossible, 1 is certain. So when we think about probabilities, we can think about them on a spectrum of, small probabilities. Probabilities close to 0 are events that are very unlikely. Probabilities close to 1 represent events that are very likely. Here's basic rule number 2. If we add up the probabilities of each of the individual outcomes in the sample space, the total probability must equal 1. Or, again, using math notation, the probability of the sample space, probability of S, is equal to 1. And then the third rule, and this is a very useful rule, is that the probability that an event occurs is 1 minus the probability the event does not occur. And we call this the complement rule. Okay? And let me take a second here to describe what the complement of this set represents. Okay, so if we think about the decision rule from the ESP example, okay, first of all, I want to write down the sample space. So there's our sample space. Now if I create a decision rule, okay, if I just create a decision rule that says reject H0 if X is greater than or equal to 7, and I think about an event like if I define event A as reject H0, then in terms of sets, H0, event A would represent the following. because 7, 8, 9, or 10 is going to result in a rejection. And then the complement of event A, which would be do not reject H0 in this example, in this case, would be everything else in S, 0, 1, 2, 3, 4, 5, and 6. Now notice all the probability rules work out here because the chance that something from our sample space happens is 1, it's certain. We could calculate the probability event A happens. If we go back to our previous example, actually, or my previous simulation, I would approximate the probability of event A as being 0 because I didn't get any results that were 7, 8, 9, or 10 in that simulation. Then A complement would be 1 minus 0 or 1. And again, I want to reiterate that when we're doing simulations, really need to do more than 200. But the calculator is limited by its memory and things like that. And really, I'm trying to get the idea across about how to do the simulation. All right, now let's talk about the fair die model again. And this time we're going to look at it from a slightly different point of view, which is actually looking at the complete sample space. So let's see. A die with faces 1, 2, 3, 4, 5, and 6 is suspected to be unfair in the sense of having a tendency towards the larger faces. And we wish to test the following hypothesis. The null would be that the die is fair, which means it has an equal chance for all 6 faces. The alternate is that the die has a tendency towards showing larger faces. And for the data, we're going to roll the die 2 times. And what we're going to do is recall that I haven't talked about this in a lecture, this is in the book, but there are 36 possible pairs of faces if you roll a die 2 times. So if you look at this diagram here, we could say that, for example, might think about this first entry here in these ordered pairs as that's the result of the first roll. So if I go down this column, that would be the first roll was a 1 or a 2 or a 3 or a 4 or a 5 or a 6 and so on. And then I can think of the second entry as the result of the second roll. So the first roll was 1, 1, and then so notice that this is how this matrix kind of breaks down. First roll 1 through 6, but on the second roll that you know, each one was a 1. Then we go across the row, we have first roll was a 1, 1, 1, 1, 1, and the second roll were 2s, and then the matrix shows all the possibilities. Okay, and one of the things to keep in mind here is that to roll a 3, now this would be this particular entry in the sample space, that would be, if we sum the pips, that would be our 2. So there's one way to roll a 2, okay, if we roll a die twice. And notice here, there's 2 ways to roll a 3. You could roll a 2 first and then a 1 next, or you could roll a 1 first and then a 2 next. And this is going to be important when we actually go to calculate the probabilities. So notice there's some structure in this matrix. So I got 4, 4, 4. Now, if you've ever played craps, this 2 and a 2 is called the hard way. So all of these along the diagonal are the hard ways. So how it's hard, and the idea here is it's harder to roll a 4 by rolling 2 2s than it is to roll a 3 and a 1 or a 1 and a 3. There's 2 ways to roll the 1 and the 3. There's only one way to roll a pair of 2s. Same thing's true for 5. Well, actually, not so, because you can't. 5's odd, so you can't have a pair. But 6, for example, it has a hard way. That would be 3 and 3. There's 1, 2, 3, 4, 5 ways to roll a 6. Only one way to do it with a pair of 3s, and so on. And so again, if you play craps, there are all those hard way bets, and the idea is that you know, the odds are against you. There's only one way out of 36 to roll a hard 6. And so I don't remember what it pays. It's been a long time since I played craps, but the odds are usually pretty good. Okay, Let's see. The sum of the two rolls will be the response used to make the decision between the two hypotheses. Okay, so that's our setup. Now, in part A, we're asked to consider the possible sum of 11. And we're going to circle the outcomes in the accompanying sample space that correspond to a sum of 11. Then we want to calculate the probability, the probability of getting a sum of 11 on the next two rolls. Okay. All right, so that's the 6 and a 5 would be 11. 6 and 5 is 11, and 5 plus 6 is 11. So there are two ways to roll 11. So I'm going to define a variable just to have something to talk about here in my notation. So x is going to be the sum of the pips from rolling a die twice. So the probability x is equal to 2 is equal to 2 ways to roll on an 11, or I'm sorry, not a 2 on an 11. So there's 2 ways to roll an 11 out of 36 possibilities. Which reduces to 1/18. Now, the suggested format for the decision rule is to reject H0 if the sum of the two rolls is too large. So what would the direction of extreme be? Okay, so now let's think about this for a second. So if the null is true, let's recall the null and alternate here. So if the die is fair, we expect to roll a 7. Oops. So if the die is biased towards larger faces in the alternate, we'd expect x to be greater than 7. So larger values of x, if the alternate's true, would be common and more unusual for the null. So direction of extreme here would be one-sided to the right. Now, part C, what is the p-value if the observed sum actually equals 11? All right, so oops, let me start over there. Try that again. Okay, so there's the definition of the p-value. P-value is a chance of sampling data at least as extreme if H0 is true. Okay, I just put p-value. I'm kind of paraphrasing. I'm using a shorthand notation, p. Sometimes we write p-value, sometimes we just write p. Now, in this case, the p-value is going to be chance of rolling 11 plus the chance of rolling a 12 two ways to roll an 11 out of 36. There's only one way to roll a 12 out of 36. So our p-value here would be 1/12. Or about 0.083 approximately. Now the part D asks the question, would an observed sum of 11 be statistically significant at the 5% level? So at 5%, at alpha equal 5%, we would say the observed value is not statistically significant. And the reason is because p is greater than alpha in that case. 8.083 is greater than 0.05. I just realized I should have written some up here. Insert it. Okay, so if alpha is equal to 0.1, the observed sum is statistically significant. Because 8.08 or 8% is less than 10%, or 8.3% is less than 10%. So we would reject the null if alpha were 0.1. We would not reject the null if alpha were 0.05. Now let's talk a little bit about some important the important concepts revolving around probabilities. First one is the frequentist interpretation. And the idea here is that we interpret probabilities as relative frequencies. So for example, alpha equal 0.05 means that type 1 errors are going to occur with a frequency of 5%. That's why I refer to type 1 error sometimes as a type 1 error rate. How frequently do type 1 errors happen? So again, the frequentist interpretation of 5% alpha means type 1 error happens one time out of 20 hypothesis tests. The other important thing about probability that you got to keep in mind is small probabilities tell us that the event is not likely. So if we think about the rare event principle in terms of our hypothesis testing, so small p-values indicate rare data given h0 is true. So what are the common probabilities used in statistics? Alpha, type 1 error rate, beta, type 2 error rate, p-values. Later on, we'll talk about something called the a confidence interval, and we'll have the level of confidence. Will come up later in the course. So anyway, those are some of the important ideas about probability and what I like to focus on, because one of the reasons you have to learn about probability in a statistics class is because there are particular what we call statistics, p-values, alpha, and so forth, that you have to be able to interpret. So, and those are probabilities. Now, the other way we can interpret probabilities, the book describes as like a personal probability, which is, you know, if I said, well, there's 5% chance of rain, then you would think about that in terms of, well, it's not very likely it's going to rain, right? But if I use that kind of in that context of whether or not it's going to rain, I'm probably not really thinking that, that days like this, one time out of 20 on days like this, it would rain. So that's more of a kind of subjective way of looking at probability. Anyhow, this does it for this lecture. So I'll see you next time.